Hi, everyone. Let's start Chapter 7 on systems and inequalities, although I'll just briefly discuss inequalities, and they won't really be on your homework. We have another blend here, section 7.1 through 7.3, kind of like in trig, and we're going to deal with solving systems of equations. Now, before, old school, you would solve just a single equation, like 2x equals 6, for one variable or unknown. Here, you're solving for x, and x would be 3. But now, we're going to solve a group or system of equations for 2 or more variables or unknowns, like, for example, a and b. And your solution, by the way, will be a solution set. Technically, up here, your solution set would consist of the number 3. Down here, your solution set may consist of one or more ordered pairs, a value for A, comma, a value for B. And order can matter. So before, we would solve a single equation for one variable or unknown. Now, we're going to solve a system of equations where our solution set will consist of ordered pairs, ordered triples, and so forth. Here, our solution in the solution set must satisfy this equation. If you plug in 3 for x, then the left side will equal the right side. Now, a solution to a system or group of equations must satisfy all of the equations in the system. So here, the value for A you get and the value for B you get will have to satisfy both the first equation and the second equation. This ordered pair must satisfy all the equations, must solve all the equations in the system in order to truly be a solution. Now, here, this is a system of linear equations. It's a linear system. And hopefully you remember this from your prior algebra classes. Well, some of the techniques that we use to solve linear systems, we're going to see again in this chapter when we solve linear and nonlinear systems. In particular, we're going to revisit the substitution method, where we solve for one of these variables in terms of the other, and then plug or sub in, and also the addition or elimination method, where we basically add equals to equals, maybe by multiplying through numbers first. So again, the techniques that we saw for solving linear systems, such as these, we can now extend to nonlinear systems. And I'm going to focus a bit more on those in this chapter. Nonlinear systems have the property that at least one of the equations is nonlinear. So you see something like an x squared or an x cubed, for example, in an equation. Let's start by solving this nonlinear system, and let's use the substitution method. The other method we'll talk about may be more appropriate if we have a whole bunch of like terms in both equations. Here, we have this x cubed term kind of sticking out there, so the substitution method might be better than the elimination method we'll talk about later. So let's solve this nonlinear system. It's a nonlinear system because of this x cubed term in particular. But my answer to a solve a system problem will be a solution set, which will consist of one or more ordered pairs of the form x, comma, y. There could be more than one solution here, more than one ordered pair that will satisfy or solve both equations. In fact, as we'll see, the solution set could be the empty set. In some cases, it's all possible pairs of x and y, or R2. Although that will be rare if you see it at all in our homework examples. However, you will see homework examples where the solution set could be the empty set, where there are no pairs x and y that will solve all the equations in the system. Let's solve this system. And we can use the substitution method. We can solve for one of these variables in terms of the other, and we can do this in either of these two equations. We can, for example, in this step 1, solve the second equation for y in terms of x. You could solve for x in terms of y, but as you might see, if you solve for x in terms of y, we're going to end up with a cube root. That doesn't seem so appetizing. So in the second equation, let's try to solve for y in terms of x. In the first equation, you could solve for either. It could be easier to solve for y. Okay, let's solve this second equation for y in terms of x. To accomplish that, we can subtract x cubed from both sides. Don't say move, say subtract. And we can add 2 to both sides. This will have the effect of isolating y on the left-hand side. And we end up with basically 2 minus x cubed on the right side. That might be a nicer way of writing that. So again, the second equation here can be rewritten as y equals, see y is all alone on the left side. After you do all this, y equals 2 minus x cubed. I'm going to circle this, and I'm going to call this star because we're going to use this later on. Notice here, we have a nice functional relationship. We have y as a function of x. That's really, really nice, as we'll see. It's really nice if you can express one variable as a function of the other. So for example, no plus or minus jazz. So here we have y in terms of x. What are we going to do? We got this from the second equation. Why don't we take this expression for y and plug in, substitute for y in the first equation? And you should do this in the other equation. If you try to plug this back into the equation you got this from, equation 2, then you're going to end up with something like 0 equals 0, and that's not going to help you any. So take this expression and substitute into the other equation. From here, we get 3x plus the y here, we're substituting with the result from star, right? Y is 2 minus x cubed. We substitute. To be safe, I put grouping symbols, but that's not so essential if you have a plus sign in front. Now, if there's a minus sign in front of the y, then yeah, I would recommend grouping symbols. After a plus sign, it's not so necessary, but I put them in just to be safe. All of that equals 2. The goal ultimately now is to solve for x. We now want to solve for x. I can remove the parentheses. We can subtract 2 from both sides. We see we have 0 on the right side. That's very convenient. On the left side, we have 3x minus x cubed. So I have this function of x equaling 0. This is a good setup. Generally speaking, if I have 0 isolated on one side, I might be in good shape. So over here, we have 3x minus x cubed. What can we do with the left-hand side? Hint, the 0 on the right side might help. We have a 0 factor property, right? Let's factor that. Now, you might be tempted to divide both sides by x. I'd advise against doing that because you're going to lose x equals 0, and it turns out x equals 0 is going to lead to one or more solutions. So don't divide by x because x could be 0. Let's factor. That's safer. Okay. Actually, before we even factor, you could factor this as is, but some of you might prefer having a positive leading coefficient. So you could add x cubed and subtract 3x from both sides. And some of you might prefer this equation over here. So it's your choice. You can either factor this left side over here, or you can factor this right side over here. This might be more familiar to you. What is the GCF? What can you factor out? You can factor out an x. And what's the other factor? Again, don't divide by x, factor out an x. And the other factor will be x squared minus 3. If you had factored an x up here, the other factor would have been 3 minus x squared. And that would have been fine as well. In either case, we can set this other factor equal to 0, 3 minus x squared or x squared minus 3. They do have the same real zeros anyway. You could also factor this. Remember, x plus root 3 and x minus root 3, that would work. But I think many students would use the zero factor property right now. So remember, x could be 0 or x squared minus 3 could be 0. X equals 0 or x squared minus 3 equals 0. There's no x term in here, so we could eventually use the square root method. We can isolate the square. Okay, isolate the square here. I can do that by adding 3 to both sides. X squared equals 3. And then remember, x equals what? X can be plus or minus the square root of 3. Please remember the plus or minus. A lot of the students forget by now. But if x squared is 3, x can be plus or minus the square root of 3. All right. So we have here real solutions for x. Are we done? Are we done? No, we're not quite done. Because remember, our system involved x and y. And our solutions, if there are any, are going to be in the form of ordered pairs. So for each of these x's, we're going to try to look for a partner y coordinate. We're not done yet. We have to find the corresponding y values. And remember, back here in star, what was great about this? The great thing about this starred guy is that it expressed y as a function of x. We're going to reuse this. It's going to be nice and clean. For each x value, there's going to be exactly one y value associated with it. And we can make a table. So in the left, again, we're back substituting into the star guy. This was my star guy, y equals 2 minus x cubed. We had 3 real values for x. When we plug these values for x into this formula for y, well, what do we get? When x equals 0, we get 2 minus 0 cubed, we get 2. And the corresponding ordered pair would be 0, comma 2. X coordinate, comma y coordinate. I'll list these ordered pairs out later because we're going to write the solution set later on. Next, let's go to x equals positive root 3. Plug in. Okay, we have y equals 2 minus the cube of positive root 3. But what is the cube of positive root 3? Well, let me ask you something. If an algebra student were to ask you, what is x cubed? What would you say? X cubed is x times x times x. Well, likewise, the cube of root 3 will be, look over here, the cube of root 3 will be 3 copies of root 3 multiplied together. Root 3 times root 3 times root 3. A pair of these will give me 3, right? Root 3 times root 3 is 3. This root 3 is also there. So basically, we get 3 root 3. The cube of root 3 is root 27, or it's 3 root 3. So over here, 2 minus the cube of root 3, that's going to be 2 minus 3 root 3. I'll put this in red. 3 root 3. That goes over here. But remember, the full y coordinate is 2 minus 3 root 3. And this is not negative 1 root 3. Do not combine the 2 and the negative 3. Do not combine these. I'll make this little mark here. Do not combine these. This is not negative 1 root 3. The negative 3 and the root 3 are tied together, but the 2 is a separate term. As for x equals negative root 3, it's going to be similar, except that we're going to have a plus sign in the middle. The y coordinate is 2 plus 3 root 3. So now let's gather our 3 ordered pairs. The first one was 0, comma 2. Let's get the other 2. So the solution set is going to be, I'll shrink this a bit. All right. So we have the braces to indicate a solution set. The first ordered pair, not that the order matters among these 3. The order matters inside each ordered pair. Don't switch the 0 and the 2, but you can write these ordered pairs in any order. But the first ordered pair I had listed here was the ordered pair 0, comma 2. That was from the first row. Okay. And then the second ordered pair we got was root 3 comma 2 minus 3 root 3. That's this over here. And then we had negative root 3 comma 2 plus 3 root 3. That's this over here. So it looks like our solution set will consist of 3 real solutions written as ordered pairs. Each solution is an ordered pair. Here's our first real solution as an ordered pair. Here's our second real solution as an ordered pair. Here's our third real solution as an ordered pair. All right. Now, as time permits, we can talk about checking our solutions. Now, if you're rushing at the end of the exam, you may not have time to do this, but technically we really should do this, especially for nonlinear systems, checking our solutions. Although I will say that, and this is another benefit of STAR, if we do have y as a function of x, a check is not as necessary. Things tend to work more cleanly. But if you're unable to write one variable as a function of another, then a check may be more necessary. Okay, but technically, it might be good to check. And sometimes it's more necessary than at other times, all right? But you could check your solutions in the given system, the original system, before you got your dirty hands all over it. All right. As you see, warning, there's a danger in trying to check solutions in a later equivalent system you've written down, because you may have made an error by that point, in which case it would not have been an equivalent system. You may have made a mistake. So you really should check your solutions in the original system, in the original given system that you got before you got your hands all over it. Okay, well, it's easy to check 0, 2. It may be harder to check the others, but 0, 2 is a quick check. Okay, so here's our original system. Plug in x equals 0, y equals 2 in both equations. We see here, we get 2 equals 2. This first equation boils down to 2 equals 2. The second equation boils down to 0 equals 0. So the solution 0, 2 checks out. It turns out the other two will check out as well, but it may take more time. Okay, next up, what are the graphical implications of all this? The graphical method. What do these solutions really correspond to? I'll give you a hint. It corresponds to something involving the graphs of these two equations. If you graph these two equations, and take a look and guess what you'd get, by the way, but if you graph these two equations, what 3 points do you think these would correspond to? That's next time.